So it's a great pleasure to introduce Johan van der Leur from Utrecht. He's been a visitor in Montreal a few times, I think, and he's a very major contributor to the theory of integrable systems. There are many things that go to his credit. I won't go through the whole thing, but he's done a huge amount of contributions to the understanding of integrable hierarchies. He's been a very frequent collaborator with Victor Kac, both on that subject and on the general representation theory of infinite dimensional algebras and superalgebras. He's also done some seminal work about Frobenius manifolds and WDVV equations, and also Pandevet. And he's an old friend, and we've sometimes had the pleasure of working together. But so it's a great, anyway, he's made many contributions. He's the one who invented some integral hierarchy, the so-called large, I don't know if everyone calls it that, the large DKP hierarchies are his invention. I think that's where we met when you came once to a conference in Montreal and presented that, which made a beautiful chapter in one of the CRM books. Anyway, so enough said. Johan, the floor is yours.
Okay. So thank you very much for the kind introduction, and thank you for the invitation to give this talk. So what I want to do or tell today is more or less work I did a couple of years ago, 2 years ago, I think, with Victor Kac. We were working on something else. And then at some point I made a claim saying, okay, these are all the polynomial tau functions for KP. And then Victor said, can you prove that? And that sort of started this work. So what I want to do, I want to give a sort of historic overview or at least tell a little bit what was known, and then say something about tau functions for KP and KDV hierarchy. And if I have enough time, then in the end, I will say something about what happens in the S-component case, S-component KP hierarchy. Okay, and these things can be sort of generalized to BKP and even to multi-component versions there. So you can do a lot. And the idea is more or less always the same, and I will give some of the ideas later on. Okay, so let me go to the first. So what is a Kadomtsev-Petriashvili tau function? Well, that's a function that satisfies a certain, what is called bilinear identity, or Rota bilinear identity. And so this is the identity here, which is the bilinear identity. And here means the residue means that you take the coefficient of z and the coefficient of z to the power -1. So this may be a bit strange because this is a function which, so the left-hand side is defined in Z inverse, and this part is defined in Z, but you can somehow make sense of this. And so I use the notation which was introduced by Sato and by Data Yimbo Kashimara and Miwa. This was sort of a shift in these times. So there are infinitely many times, T1, T2, etc. And this is sort of a shift. And already in beginning, this was, Sato showed this around 1980, I think. And already then he showed that all the Schur functions which are connected to partitions are KP tau functions. So let me explain a little bit what are the Schur functions. Okay, so first of all, there are these elementary Schur functions, and they are defined by this equation. So the variables are T1, T2.
Johan, you're missing the powers of Z on the left.
Oh, yeah. So you're right. Yeah. So there should be Z to the power I behind this. Yeah. Okay. And so if you develop this as some power series, then the coefficients are these functions, these Schur functions. And then for every lambda, you have such Schur functions. And this is in fact a determinant. So what you do is you, so you have a matrix, an m by m matrix, and inside you have these elementary Schur functions that somehow depend on the partition. So under the diagonal, you find the Schur functions, which correspond to the partition here that we have here. And if you go up or down, they go down a little bit with one step, or they go up with one step. And the same to the left and to the right. But what is important that on the diagonal, you find these S lambda. Okay. And then, so what is a Gelfand-Dickey tau function? A Gelfand-Dickey tau function is also a KP tau function, but it satisfies more of these bilinear equations. And in fact, so you take a positive integer n, and you assume that this holds. So this is KP if j is equal to 0. And but you have more of these powers here. So also c to the power n, c to the power 2n, c to the power 3n, and this should hold for all j. So 0 is a KP hierarchy, and then this other will give some reduction. And there's this well-known special case, the Korteweg-de Vries hierarchy, KDV hierarchy, where this n is equal to 2. And this is, in fact, in the case n equal to 2, a lot was already known. So let me give some slightly more. So what does this mean? I mean, if you look at this equation, you can somehow show that if this is 0, that this means that the tau function that we have, so this function here, that if you differentiate to one of these tjn, so tn, t2n, t3n, that you get the tau function back times a constant. So it's more or less exponential in these particular times. And all the other times they are, so this tau function is different. And this cj, this is some constant, and here it's a complex constant. And Victor and I, so Victor Kac and I, were interested in polynomial tau functions. And of course, if you look at polynomial tau function, this cannot hold except when Cj is equal to 0. So for polynomial tau functions, this Cj is 0. And sort of the method that I show, you can also do this for a non-polynomial tau function. But in general, I mean, so the formulas that we get only hold for polynomial tau functions. And you should do something else in the sort of, if you want if you want soliton type tau functions or of other type of tau functions. Okay. So this is the Gelfand-Dickey hierarchy, or the Korteweg-de Vries hierarchy. And okay. Now, in this special case, when n is equal to 2, Katz and Peterson showed in the, I don't know, in somewhere in 85 or so, that that all the polynomial tau functions of the KDV hierarchy are of this form. So this is a Schur function, but it's a Schur function which is related to this very special partition, namely k minus 1, k minus 2, etc. until n. So it's more or less a staircase. I mean, and what they did, they showed that if you plug in this constant, you can plug in constants, and then you get all the tau functions, all the polynomial tau functions. So for all k and all these constants, you get these tau functions, and they're all KDV tau functions. And this is a bit strange because if you look carefully, I mean, what was it? If I go back, so let me go back. So this was the condition for a KDV tau function. where the Cj was 0. So for KdV, we see that if you differentiate the tau function to T2 and to T4 and to T6, that this should be 0. Now, and what I have here, I mean, there is a T2 and a C2 and a T4 and a C4, but somehow they do not appear. I mean, although they appear, I mean, this is a determinant of elementary Schur functions. They appear in these elementary Schur functions, but in this special case, they simply disappear. They are not present. So what I mean is, if you do this, or you plug in 0 on the second place and 0 on the fourth place, then this is exactly the same. I mean, simply this tau function does not depend on T2 and does not depend on T4. And although you plug this, you can plug this in here. Okay. And then the question, of course, was what happens in the KP or the Gelfand-Dickey case? So Gelfand-Dickey means that the n that we have is greater than 0. And of course, you could make some guesses. And so let's first go to KP. So the first guess would be just imitate what Kac and Peterson have. So just take this as lambda, and we know that as lambda for the times t RKP tau function. So what happens if you do this shift? So if you take T1 plus C1, T2 plus C2, will this be a tau function? And indeed, this is a polynomial KP tau function. That's important. But unfortunately, you do not get all the polynomial tau functions. But in fact, the guess is not so bad, as we will see later on. I mean, doing this trick, plugging in T1 plus C1, T2 plus C2 is not so bad. And it's very close to the solution. But somehow there are some reasons why, there is some counting argument. I will come back to that later. And you can see on the basis of that counting argument that you do not get all the tau functions. So, so what would be a first guess for Gelfand-Dickey? So let's go back to this reduced hierarchy or this KdV hierarchy. So KdV was n equal to 2. Gelfand-Dickey is for arbitrary n. So what happens if n is bigger than 2, right? And so the idea could be just find all Schur functions that are n Gelfand-Dickey tau functions. And then the second step could be shift all the times by this Ci, right? So let's try to solve the first question. So find all Schur functions, so functions that depend on lambda, and try to find which one belong to this Gelfand-Dickey hierarchy. And in fact, there's a restriction on the lambdas that you can choose. And the restriction is as follows. I mean, if you have a lambda, you can make some other sequence of integers, and somehow you can show that if this sequence of integers, so lambda 1, lambda 2 minus 1, lambda 3, until lambda m, and then you go down without sort of jumping. If you subtract n of each element in this sequence, then this should be a subset of v lambda again. So if you subtract of lambda 1 n and of lambda 2 minus 1 n, then this should be a subset of all these elements that we have here. Then this should be a subset of v lambda. If that is the case, then this is a Gelfand-Dickey tau function. And there are some reasons for that. I mean, behind this is some semi-infinite wedge space or some Dirac, and you can sort of show that this has to hold. So this is the first step. So this is the answer to sort of the first part. And then the second step is, so it's Gelfand-Dickey if you can subtract that. So then the second step is just we substitute for this T1 plus C1, T2 plus C2, T3 plus C3. And indeed, this is again sort of periodic, and indeed this is a Gelfand-Dickey tau function. So this solves it partly, but again, so this was enough in the case n equal to 2, right? N equal to 2, we had this lambda, which was k minus 1, k minus 2, k minus 3 until 2, 1. So it's sort of a staircase partition. In this case, and in that case, if you did this substitution, so replace T1 by T1 plus C1, T2 by T1 plus C2, you got all the possible polynomial tau functions for all these lambdas that are possible. In this case, unfortunately, this is not the case. So you get some class of polynomial tau functions, Gelfand-Dickey tau functions, but you do not get them all. And that's a bit unfortunate, but yeah, how can you solve this? Well, let me first give the solution in the KP case.
May I interrupt you? Only to make sure I understand the definition of the V lambda. Is V lambda a set of m tuples, or it's an infinite set of integers?
Yeah, in principle, it's an infinite set of integers. But from this point on, it goes down. It goes minus m minus 1. So there are no holes. So here it can jump, right? It can be 5, 2, and then, but here at some point it simply jumps, right? So this lambda is finite somehow. It's a partition. Then you make this sequence, and then if you subtract n from that, you get this. So let me go back to, for instance.
May I just make a comment for Yvonne? It saturates. You never get, there are never negative elements. So when it reaches 0, then there's only zeros.
Yeah,
well,
but
there's only a finite number of positive. There's only a finite number of positive elements.
Yes.
And that's called the.
That's right. So there's only a finite number of conditions. The periodicity imposes only a finite number of conditions, right? Am I correct to say that the number of conditions on the lambda i's is finite?
Yeah. For this to satisfy. So if n is 3, then you could have say lambda equal to 7. But then if you subtract 7, if you subtract 3 from that, then lambda 4 must also appear here. I mean, 4 must also appear here somehow, right? And the same for this one. If you subtract 4, then it should also appear here. That's the condition. Okay, so it's sort of quite strict in this case. And so what is the solution in the KP case? In fact, it's given in sort of these elementary Schur functions. So what we have here is sort of this elementary Schur function. But what we do is that for every, and now I have to think, every column, more or less, we change the t with t plus cj, c1j, c2j. So in every column, we substitute instead of t plus c1j, and then t2 plus c2j. So in every column, it's a different constant that you add, more or less. And if you do that, then this is again a polynomial tau function. You can show that. And in fact, these are all the possibilities that you can, all polynomial tau functions. If you have a polynomial tau function, then it is of this form. There are no other polynomial tau functions. So this is pretty close to more or less the substitution in this S lambda, more or less, because this is, I mean, if you would put all the C's equal to 0, you would have this S lambda here. So this is pretty close to sort of the first guess, except that the substitution that you have to do depends on the columns. So in each column, you have to substitute another variable, more or less. Add this another constant. And the Cj's, they are sort of arbitrary constants. And since this lambda is finite here, only finitely many of these Cj's appear. I mean, in principle, these T's are all infinite, but I mean, it's a finite polynomial, so only finitely many of these T's appear, and only finitely many of these C's will appear. Okay. Well, let's do the second guess for this Gelfand-Dickey hierarchy, or this tau function. So, of course, we saw that if you take this lambda, which has this special property here, this n-periodic partition, more or less. So, so this was this condition with this v lambda. So if you have this sequence and you subtract the n, then it should be, again, be an element of the sequence somehow. So if you take a lambda that satisfies this condition, and you do this substitution, so you simply change T1 by C1j, T2 by C1j, C2j. So depending on the column, then this is again a tau function. But unfortunately, in general, it's not a Gelfand-Dickey tau function. It will be a KP tau function, but it's not a Gelfand-Dickey tau function. It depends on the times Tn in general, if you would do this. So the guess in this case is wrong. So we have to do something else.
Johan, could I just ask, your conditions imply, don't they, that it's a strict partition? You never have two equal, do you?
Yeah. It has to. Yeah, I think so, right? Yeah. No. Is it? No, I don't think so. You can have 2, 2, and then.
You can have two consecutive ones equal.
Yeah. If you would have 2, 2, and then say you subtract 10, this will be a Gelfand-Dickey tau function.
Oh.
Because if you subtract, it will be 0, right? So this lambda does not have to be strict. So it is strict in this KdV case, but it is not strict if n is 3 or n is. But I think that the number of parts that this can appear, I mean, is n minus 2. So in this lambda, probably only n minus 1 of these lambda i's can be the same.
So it's sort of a generalized staircase where the steps can be higher, but only limited by n minus 1.
Yeah, sort of. In principle, you can figure out what it is, but it sort of, we found it most convenient. I mean, sort of using this sequence. But for any n, you can figure out which lambdas are satisfy this condition and which not. Okay.
One more question from someone who's not familiar with the subject. Is there really, in the first formula, are there commas between the 1 and the j, the 2 and the j's?
Okay. In which formula?
The first one. On the right-hand side, you add to T1.
Comma, right? So it depends on the times. This is T1j, right? But this is constant. And this is a constant.
But there's no comma between the 1 and the j. You multiply the number 1 with
no.
j.
No. There's a comma. There's a comma. So it's really coefficient. So for every column j, you have a C1, a C2, which are all for different columns. They are different.
Okay.
That's the point.
Thanks.
So the Cj are sort of, for every Ci, you have these infinitely many constants, more or less. So for every column, there's a infinite series of constants, more or less, but only finitely many appear in this case because it's polynomial. And but in principle, you do something like this.
A Cij is in principle an infinite square matrix, but only a finite part of it appears.
Mm-hmm. Yeah. So what is the theorem in the N. Gelfand-Dickey case? It's as follows, and it's kind of So first of all, this lambda that we have should satisfy this condition. So it should be n-periodic. And then what we do is that the C, sort of this lambda, this is related to the column that we have in this determinant. So for each column, the C's, the Ci bars are the same, more or less. But there's some periodicity here, and it's as follows. So in here we call the C lambda I minus I plus 1, and here lambda I minus I plus 1. I mean, you do the same, or maybe this should be, this should be, no, this is correct because it's the same column, more or less. What you do here is that there's some periodicity. So this depends on, this bar means that you take it n-periodic, right? So if n is 4, and this would be 7, then this would be C3, more or less. This would be 3. And again here, this could be the same C3. So you only have sort of n of these infinite series of constants. And in fact, it turns out that only n minus 1 appear somehow. So you cannot choose them really arbitrary, but they depend on the lambda, more or less, that you have, right? And only, although this can be a 100 by 100 matrix, if this is if n is 10, only 9 of these C, infinite series of C, appear somehow. So it's really restrictive, and you cannot get other tau functions. I cannot, if you substitute something else, if you would substitute this arbitrarily, then this would not be a Gelfand-Dickey tau function. It will be a KP tau function, but in general not a Gelfand-Dickey. So it's really an extra restriction on these constants C. So this means that they should be, that you calculate this modulo n, this bar. Okay. So let me go back to this KP hierarchy and sort of show why we know that these are all the tau functions. At least in that case. Well, what is well known is these tau functions, they form a group orbit, and they somehow form a group orbit under an infinite dimensional Lie group, GL infinity. So you have infinite matrices with on the diagonal mostly ones, and they're all within a block around the diagonal, and they go to infinity in both directions. And somehow there's this group acts on one, and in this way you get all tau functions. And now looking at this group, you can look at what is called the Shubat cell. So you can take the Bruhat decomposition of GL infinity and somehow use that to calculate the orbit. And so if you do this, if you take the projective version of this, then you can show, or it's well known in this case, that this orbit consists of cells, Shubat cells C lambda, which are parameterized by partitions lambda. And in fact, this is a disjoint union. And you can show even more that what is the dimension of this C lambda? Well, the dimension of this C lambda depends on lambda. So it's really the sort of, you add all the parts of the partition. And so the dimension of C lambda is exactly this number. And now if you take this lambda, so this partition lambda, and you calculate such a determinant of S of this lambda, so this is this Schur function connected to lambda, if you put all the C's equal to 0. And you can show that this is in this cell, so this element. So if you substitute in every column different C's, then you can show that this is really in this cell C lambda. And what happens is that this fact and sort of the form of these tau functions, using this, you can conclude that we really have all the tau functions here, that nothing else is possible. You can do some sort of a Gauss elimination on these tau functions, and then show that exactly the dimension of this space is exactly this lambda.
So is it right, Johan, that the only polynomial KP tau function in the big cell is the constant?
Yeah. Yeah, and in this case it is. Yeah. That depends what you mean in the big cell. So you have to think here that what we have here is sort of this GL infinity. You can decompose this in sort of a diagonal matrix, an upper triangular matrix, and a lower triangular matrix, and take the product of these three things, right? Well, this upper triangular matrix, if it acts on this one, acts as the identity more or less, or you get, then this diagonal matrix is sort of an element in the Weil group, and you get this partition, or you get this Schur function as lambda. And then with these lower lower triangular matrices, you can let these ones act on this as lambda, and you sort of build the whole cell from that. So you go up more or less. So this S lambda is really the lowest element in this cell. And from that you build up everything.
But I think I just mean C null set, lambda the null part.
Yeah, I understand. But that depends how you define, because you can have something where this coefficient is non-zero, but you would have lower terms as lambda, right? So it really depends what you call the big cell. I mean, if you talk about projections, then I don't know. Then there are maybe more.
Okay, we can talk about this after.
Yeah, okay.
The big cell, finite dimensions and infinite dimensions, is everything that is the graph. I mean, in the Grassmannian terms, it's a graph of a map. It's the graph of a map from H to H.
Yes, but you have to think here that this S of lambda is really the lowest element in the cell, and from that you can get sort of other elements which are, well, with smaller S lambdas, right? Which is, I mean, you can build this tau function.
Oh yes, of course. Sorry. The lambdas could all be 0, but the I minus j could be some positive number.
But if all the lambda j's are 0, then there are zeros on the diagonals and below or above.
No, it's
so
one.
The determinant will be 0.
One's on the diagonal.
Yeah. One's on the, okay. Yeah, but then it's a constant, right?
Yeah.
Okay. So these are more or less all the possibilities in this KP case. And in fact, you can even show a one-to-one correspondence between this set. So there's a setCij's of all these constants, where these J run from 1 till m, and these i's are sort of between certain numbers which are given by these lambda j's, and certain cases should not appear. Well, if you count the dimension of this space, then it's exactly lambda. And in fact, there's a one-to-one correspondence between this set and all the possible tau functions. So in general, if you do any substitution here for these Cj's, you can haveCij's which give the same tau function. So differentCij's which can still give the same tau function. But if you choose the set like this, then there's a one-to-one correspondence between this C. So if you have a different set here, then you will also have a different tau function. Then the tau function will not be the same. And how can you calculate that? So what you have to do is the following. So you have these T lambdas, and you plug in these constants here, but then somehow this I that appears here should not be equal to this condition. So you simply calculate the tau function, and then you have to eliminate somehow these elements. And this is the way that you can do that, by simply substituting this equation. If you substitute this equation somehow, right? So these are expressed in lower J's, Cj's, which are sort of lower, right? So so with this you can eliminate this variable, and you have to do this recursively. So you first start with the smallest one, and then the next one, and then the next one. And then you really get a one-to-one correspondence between theseCij's that you have here and all different polynomial tau functions. So this is really a one-to-one correspondence. Of course, what happens is, I mean, you can always multiply a tau function by a constant, but somehow we want to avoid that, right? And we want, we do not want that somehow. So if you forget this constant, so up to this multiplicative constant, there's a one-to-one correspondence between these sets and all the different tau functions. Okay. So let me give a sketch of the proof or how you can show this. And so what is behind this is this, what is called this Boson-Fermion correspondence, or well, a Clifford algebra and a representation of this group real infinity. So what we consider is Clifford algebra on generators psi I plus and minus. So there are infinitely many of these generators, and they satisfy this equation. So lambda and mu is either plus or minus. And for some reason, I prefer to have this I in 1/2 plus z. You can do this differently. And so they are paired more or less. If I is, so lambda should be equal to minus mu. So you get 0 except when lambda and mu is plus minus or minus plus, and when I is equal to minus j. So this is Clifford algebra, and this sort of gives the bilinear form on this Clifford algebra. And then with this Clifford algebra, you can define what is called the spin module. And so you take a vacuum vector, and you say that all psi j's acting plus or minus j's on this are 0 if j is positive somehow. So all the negative j's, psi plus and psi minus, they build the whole module, more or less. And in fact, you can show that in this Clifford algebra, we get this KP equation is the following equation. So you sum over, so you take the tensor product of 2 of f with itself, you take a certain function in that set, okay, it has to be in the 0 charge sector, but I don't want to go, or in some other charge sector, but I don't want to go into too much detail. And then this should hold somehow. So there's the sum of psi j acting on tau, tensor psi minus j acting on tau. This is 0. And And that's sort of the equation that we had before, but now in this language. So this, in fact, will be the bilinear equation for this tau function, although it looks quite different. And then it's sort of known because behind this there's this semi-infinite wedge space, or this Clifford algebra, or this is spin module of this Clifford algebra, or something which is called the hierarchies. And you can simply show that a polynomial tau function should correspond to the following expression. So what you do is you let a number of vectors act on it, and these VI's are of this form. And these are the only possibilities to get a polynomial tau function. First of all, it should be, you're not allowed to take an infinite vector somehow, but only a finite vector. Yeah, so this holds. And I want to make a restriction. First of all, I assume that Vi depends on Ni, and I assume that V1, that N1 is bigger than N2 is bigger than N3, etc. And then I do another restriction, which simply only changes the tau function by a multiplicative scalar, is that I assume that the lowest AJI that appears, or the psi j that appears, this one I choose 1. And this sort of, well, is a restriction, but it only gives a tau function up to a multiplicative scalar. So this is not really a big restriction. And this, I mean, these V's you can simply order that they are of this form. And if you interchange 2, you get a minus sign somehow. Okay, so this is a polynomial tau function. And then there's this, what is called this Boson-Fermion correspondence. This spin module for the Clifford algebra, you can realize in a different way. So as some polynomial algebra in the T's and some, well, Leur polynomials in Q and Q inverse. Right. And this is the way that this isomorphism is described. Namely, if you take these psi plus and minus of z, if you turn this into some field, some generating series, then this generating series for both plus and minus is equal to this expression, to this operator acting on, well, the identity on 1. So we assume that the vacuum vector goes to 1, and then this psi plus or minus z has this expression. Okay. So this is more or less this Boson-Fermion correspondence, this link between this spin module and on the other hand these Laurent polynomials in Q and polynomials in T. Okay. And so such a VI, the VI was some finite sum of psi pluses. Okay, so you simply take this expression. So let me go back. So VI is this. So there are only finitely many AJIs. And so you can force that by taking this field, this generating series, putting it there, and then multiplying this with some function in Z, where only some polynomial in Z, where, well, okay, maybe finitely many positive and negative terms of powers of Z somehow. So these VI's are of this form. And then you can show that if you use this Boson-Fermion correspondence, so this isomorphism between this spin module for this Clifford algebra, and on the other side, this spin module, polynomial algebra in the T's and in the Q's, you can show that this thing is this Wronskian, and now I make a mistake because behind this should be Q to the power M. So but this Q to the power M is not so important. I mean, you get this Wronskian of certain functions. So the Wronskian means that you have, that this is a determinant of certain functions where in the first row you take these functions, and in the second row you differentiate to T1, and in the third row you differentiate twice to T1, and in the next row you differentiate once more and once more. Where these Fi's are these expressions. So remember that these Aij's appeared in these Vi's, and so somehow these Fi's that we have here sort of form this, well, these Vi's, but now in this polynomial algebra in the T's. So Vi's really give this expression. But this expression is, here there are these elementary Schur functions. Remember, J is 1/2, is an element of from 1/2 plus Z. So this will be a positive integer somehow. So here you have a finite sum of these Schur functions, of elementary Schur functions. And the trick that we used is that this is equal to the biggest one that appears here, which has coefficient 1, because we chose this to have coefficient 1, and then that you change this with certain coefficient Ci. So let me show that why this is the case. And this is, in fact, almost trivial, because what we use is this x to the tj z to the power j, they generated these elementary Schur functions. So if you change this by Cj, you get the elementary Schur functions, but then with this shift. So t plus c. But these are the exponentials of a sum. So you can split this into two exponentials. So an exponential of only the t's and an exponential of only the thing with the z's. So if you do that, you get this expression, right? And then collecting sort of the term of z to the power k, you get some expression here. And this gives that this fi of t, which was this expression, now is equal to this expression, to the sum of products of these guys, more or less. So here it's in the times, and here it's in the constant. But now you can, but this is equal to that. So what you do is you have these constants a, and here you can solve this recursively. For you start with L equal to, you start with L equal to ni minus 1, and you find a C1 such that this holds. And then you do the next one, and you find C2. And then the next one, you find C3. So you can really solve this recursively, more or less. But this is the idea behind it. So this expression, this which we have here in this Wronskian, you can really write this as only one Schur function, but then shifted by these constants. But you have to do this for every f differently. You have to take different constants for every f. And this is sort of the proof, because these Wronskians that we have here are these Schur functions. If you plug in this, it will be the Wronskians of Schur functions, but this will be this S of lambda, where you have this shift in this, where you replace this t by t plus a constant, but you do this for every column different. Right? So for every column, you have to choose different constants and you plug this in. So this is sort of the idea behind this. This is more or less the proof and that this holds. And in fact, that you really, if you look at it, these ni, so the ni minus 1, they determine the partition more or less. So this will determine the partition. It's not exactly the lambda I, but it's a bit bigger. So on the diagonal will be the lambda i's. So if you write down this Wronskian, then and you plug in these functions, then on the diagonal you have the lambda i's. But for every column you do a different shift in the constants. And what you can do is you can simply use, I mean, if you go back to these VI's, so here there's an expression, But since this is a Clifford algebra, you can sort of use Gauss elimination to remove certain aij's. I mean, you simply write this as a matrix and then do Gauss elimination to make as many zeros as possible, and that's possible. And then you can count, and then you see that effect you get, if this somehow corresponds to this S lambda, that the dimension is really lambda. So it's really, sort of based on sort of this trick that if you have such a function, you can write this as one Schur function, namely the biggest one that appears here. But then you have to substitute instead of t plus c of certain constants. And you can solve this recursively. That's the idea behind this. Okay, I don't know if I still have some time. I could explain sort of what happens in the S component case, if you would be interested. But I can also stop and answer questions if there are questions.
Well, you haven't used up your time. You have, we started 5 minutes late. You have 10 minutes left.
Okay. So let me do the S component case. It's only 3 pages. It's slightly more complicated, but the idea is the same, more or less. So what is the S component KP case? In fact, instead of one tau function, you have a whole collection of tau functions that are somehow connected. So in the S component case, there is sort of a lattice which plays a role. This lattice, and so let me write this as a vector in this lattice, more or less. And then using this notation, so if I write R with this, then I sum all these elements in C to the power S. So if I write the absolute value of R, and if I write Rj, I only sum the first j minus 1. So this is just adding them up, and if j is 0, then Rj is 1, then this is 0. Right? So then the S component KP hierarchy is a collection of tau functions, tau R, so they depend on this lattice. So, but there's a restriction. The absolute value of this R should be K. Right. By the way, these R's can be negative, right? So you really have to. I mean, you can. So there are many possibilities, and so for fixed K, this is the following identity holds. So it's a bit similar. So in the one component case, this S was 1. So you have only one of these infinite time flows, more or less. But here we have S of these infinite time flows. And somehow there was only one tau function, but here is some combination of tau functions, and you have to sum this. So this collection of tau functions are somehow related, and you want to solve find all polynomial tau functions that satisfy this equation. And in fact, this is, in terms of this Clifford algebra, nothing changes. I mean, the S component case or the one component case or the two component case is completely the same in terms of this Clifford algebra. The only thing that you do is that you define a different gradation on this space. So the one component KP hierarchy has a different gradation than the two component KP hierarchy and the S component KP hierarchy. And this has all kinds of, so in the spin module, it's the same, except for the gradation. But if you realize this as polynomial, in this polynomial algebra, so using this Boson Fermion correspondence, then one component and S component are really different. But they describe the same group orbit, and that's an important feature. So here is this expression somehow in different taus. And then, of course, the question is, what are the polynomial solutions? And in fact, these are the polynomial solutions. So it's sort of a Wronskian here. But the difference is that you, so the matrix is a K by K matrix, I think. And you add it in such a way, so M1, you differentiate M1, or so you have K different kind of functions, HT, which depend on all these on these S infinite time flows somehow, and you differentiate the first one to M1, this one to M1 minus 1 until T1, and then you do a block with these T2. So this depends on M1, M2 until MS, right? So you really divide it into this way, and you should keep the order somehow, because all these tau functions, they depend on a sign. And if you change the order, then the sign changes, and then they do not longer satisfy this equation. So somehow you should stick to this case. So this is sort of the generalization of the Wronskian we had before. And what are these H's? Hj. This Hj consists of elementary Schur functions, but then S different ones. So you have S different ones, where in each A, you substitute TA. So you substitute this infinite time series, which belongs to either T1 or T2 until TS. And this you substitute. And then, so you also have infinitely many of these CJs. You have, for every column, you have S of these infinite CJs. And so the formula is more or less similar, except it's more complicated. And yeah. And again, you can show that these are the only polynomial tau functions that exist. And of course, it's collection. So for every, so there's a whole collection of M's for which you can calculate this. So you should fix H1, H2 until Hk. And this defines all the tau M's sort of that appear. So this is general case. So it's slightly more, it's more complicated. When sort of doing this one component case, I thought this would never be possible to do because it would be too complicated. But in fact, the idea is more or less the same. So the idea is the same. You have this spin module, you have these vectors, and you simply figure out what these vectors are if you go to this polynomial algebra, to this lattice and these times, and in fact you get this solution. So it's slightly more complicated, but the idea is really the same as in this one component case. Okay, so that's more or less all I wanted to say. Thank you for your attention.
Thank you very much.
Okay.
Thank you.
So is William going to ask for questions, or should I ask for questions?
You can ask, John. I mean,
all right.
You're more of an expert than I am.
Question.
Yeah, I have actually a question. So, for example, Marco Bertola here. Sorry, can I ask? Yeah.
Yeah, sure.
So, for you know, are you familiar with these Vorovets-Jablonski polynomials that are then actually the source of rational solution of Painlevé-2 and the Painlevé-2 hierarchy?
No, not really. Well,
no, okay, so but then they are essentially the polynomial tau function of a KDV hierarchy.
Okay, yes.
So then my question along these lines would be whether these other polynomial, or all these classification of the polynomial solution may be of use in classifying rational solution of Painlevé, of certain, at least Painlevé hierarchies. Probably Van 4, Van 5.
Yeah. No, this I only know Van 6 because I did some work on that. And in fact, so I think Van 6 you have to do. I think 3-component KP or something, or n-component KP, and you do something there, but you really have to take a very special case.
Right. That's right. So what I'm saying is that the classification of rational solution may actually be a sub classification of these, right? So that might be interesting.
Yeah. So I did some work with Hendrik Aratin on that, and what we did, we started with this, this Frobenius manifold. So you have this Darboux-Egorov system, and this Darboux-Egorov system is somehow a subset of this S-component KP. It's this n-wave equation, but you have to take certain restrictions. So what you have there, you have this GL infinity, but you can also in this S-component case, but you can restrict this to what we call this twisted loop group. So you have this symplectic structure, and you get this loop group. So, and then in that case, you have many tau functions, but if you pick out the one which is, I mean, you have a matrix of tau functions, but if you pick out the one which is around the origin, then this is the one that somehow corresponds to Van 6. In a certain case, I forgot exactly which one, but we wrote some paper on that. And in fact, there are sort of back loop transformations that you can do, but it's only rational solutions.
Rational solution, right? Yeah. Okay. All right. Thank you.
It's connected to Van 6, and in fact, you do not have to take this Darboux-Egorov system, because in this Darboux-Egorov you assume that these that the elements are symmetric, more or less, and this you do not need. So you can really take the n-wave equation, more or less, and use that to get solutions. But I forgot exactly how this works. But there is some transformation that you need to do, and then you get these solutions. And of course, you only get the rational ones. So you have the ones which are on the. I think that they're really on the corner of the while group, right? I mean, so not on the so if you so in the corner of the chambers, I think that you have they correspond to, as far as I remember.
But Johan, if I could make a comment, the work that you did with Aratin.
Yes.
By the way, Marco, this is exactly what I was suggesting that we look at. That work, you essentially reduce the whatever S component KP with some kind of multi-scaling reductions to get the WDVV equation.
Yeah. But this is sort of this Darboux-Egorov system, right? That you,
right. But was there anything requiring that should be polynomial?
Well, at least in our case, we only had very simple elements. So we only took elements in this twisted loop group, which had sort of diagonal and had C's on the something only on the diagonal, something Z to the power A or something. But then C to the power A and C to the power minus A should appear on this diagonal.
But are you saying that the solutions to the WDVV equations that were obtained by reduction of S component KP were all polynomial?
Well, that depends. I mean, if you want this homogeneity condition, then this is a very, very big restriction. If you forget that, then you can get more restrictions.
Well, you need the homogeneity in order to have a relation to the whatever Schlesinger or isomonodromic systems. That's the point. So, but are you saying that the only isomonodromic solutions that you obtained were polynomials?
Yeah, I think so.
Oh.
Well, the tau functions were polynomial, but I mean, if you I mean, you take the ratio of two polynomial tau functions. These are these.
No, I'm speaking of the tau functions.
Yeah. I think so. And they're really very simple. I mean, thinking in terms of this loop group or twisted loop group, you only take elements on the diagonal. So
I just realized that. I mean, we're with, I don't want to take up everyone's time, but with Marco and Fabrizio, we're actually trying to understand better this question of multi-scaling, well, relating the KP or multi-KP systems to isomonodromic systems. Well, your work with Aratin is really an inspiration for that, because I thought that was the only rigorous results which could reduce these autonomous systems to non-autonomous isomonodromic ones.
Yeah. But I think that what we consider there, because you really needed this homogeneity. I mean, in this double Egorov system, you wanted I forgot because it's a long time ago that I did this, but this gamma ij should be degree -1 or something, or something like this. And then there's not a lot of choice. I mean, as far as I remember.
Well, you definitely need the homogeneity condition, because that's what gives you an operator in the spectral parameter whose monodromy is invariant. Okay.
Yeah, but yeah.
Let me slip in one other. Maybe I don't know if everyone is interested in this so much, so we could continue speaking after the formal talk is over. But I'd like to slip in one comment before everyone leaves. And I mean, you know this, but I think I want to say it. These solutions that Johan gave, I mean, the polynomial solutions to KP, in some sense, these solutions were long known. It wasn't known that these are all the solutions, but the existence of these solutions were long known in a different, slightly different formulation. And that is the following. When Johan uses the KP flow variables T, well, of course, everyone who's studied symmetric functions and thinks of Schur functions as symmetric functions, you know that these T's are not really the independent variables as symmetric functions. They are the power sums in the other variables. So if you look in McDonald's book, you're really looking at the Schur function not as a function of a number of indeterminants, a symmetric function, but as a function of their power sums. But if you go back, I mean, the formula that Johan gave, that's known as the Jacobi-Trudi formula, which expresses the Schur function as a determinant in terms of what he called elementary, but actually are complete symmetric functions.
Okay.
But there's another formula due to Jacobi, which is the oldest formula for Schur functions, which is essentially the same as the Weil character formula, which expresses it, of course, as the ratio. It's the bi-alternant formula, and it expresses it as the ratio of two determinants of the alternate form, which is a special type of determinant. The denominator is just the van der Moon determinant, and the numerator is a determinant formed from homogeneous polynomials, just actually monomials in the auxiliary variables. But that only works when you have a finite number of auxiliary variables, whereas Johann's formulas do not make any such assumptions. So they're valid, they're polynomials in the power sums. But of course, they're also polynomials originally in these original variables in which these are symmetric functions. Okay, so what I wanted to say, I'm going to say this very, very quickly, is that the polynomial KP tau functions that Johan wrote down, if you wish, they can also be written like Jacobi did for the Schur functions in a bi-alternant form. And the only difference between the Schur functions and these generalized polynomial tau functions is that instead of the entries of the numerator determinant being monomials, they are arbitrary polynomials. And the coefficients of these polynomials are closely related to those constants Cij that.
Sure.
So that's a fact that those formulas, those bi-alternate formulas for polynomial tau functions were known a long, long time ago. Special cases were studied by Luke and Biedenhardt, And actually, we, with a postdoc about 12 years ago, we wrote that down, but I think other people knew these formulas. But nobody knew until Johan and Victor proved it, that this was everything, that there's nothing else. So that's quite an accomplishment.
Oh, but I guess this was expected, right? Because this was the claim I made to Victor. I said, I think these are all the polynomial tau functions. And then he said,
but you proved it. When we were thinking about this recently, we were scratching our heads and saying, well, these are polynomial tau functions. Is that everything? And we didn't know. But then we looked up your paper and saw that you had proved it. Okay, that's all I wanted to say. Okay. Of course, for the we can continue talking, Johan, after we've dismissed everybody else. But for the non-specialists, Johan knows about all of these integrable hierarchies. He's only mentioned 2 or 3 of them today. But there's also the BKP, the CKP, the DKP, then the I don't know what other variants there are. And he's got similar results with Victor and by himself on all of these hierarchies. So there's really quite a landscape of such polynomial solutions to different hierarchies. And in particular, there are very analogous formulas to these Jacobi formulas, which hold for the BKP hierarchy and the so-called Schur Q functions. Okay, I think that's my question. Does anyone have other questions? Is anyone still on board? Yeah, I guess you are. No other questions? Okay, then how about if we thank the speaker?
Thank you. Thank you very much.
And let's not all sign off, but those who would like to continue. Johan, are you okay for another 10, 15 minutes discussion?
Yeah, that's fine.
Yeah, good. Okay, so
not so late yet as I expected.
Yeah, it's 1 hour earlier, so
yeah.